Hi, everybody. Today I am gone, um, and we're going to do a bunch of stuff where we're looking at the beginning of chapter 7. Um, so I'm going to talk for a little bit, and then you can do some stuff on Desmos, and then you're going to have a little practice assignment. So here we go. I'm gone. I'll be back tomorrow. My wife and I are closing on our house, so we are officially going to be homeowners, which is very exciting. I will most likely have your tests back to you on Friday. I just have a busy week, and so I'm going to try to be a little bit forgiving for myself and give myself a couple days to get you your tests back. Sorry that it's not like immediate, but you'll be all right. We're going to talk a little bit more in the future about what corrections and retakes look like when I get back. So bear with me on that. Okay, so the first part of the unit is about exponential growth. There are three equations we're going to use a lot for exponential growth, and we're going to look at a lot of graphs today. So we're going to start with that. Just so you know, for all of these equations, the R is an interest rate or a percent increase or decrease. Okay, so while it says R is a percent, you actually have to rewrite it as a decimal. So if I have like a 4% interest rate, remember that the word percent means out of 100, and so 4% is 0.04. So we'll be using this and not this in the formulas. Okay, we can use all these formulas to model exponential growth and decay, which means, something grows and then as it grows, more things grow because of the previous growth, which is a little bit of a weird concept, but we saw a lot of that in the development of COVID in the beginning of 2020 when COVID was like nobody had any ways to stop COVID. And so it just grew uncontrolled for a long time. And that was exponential growth. So, yeah. Anyway, those are some of the ways. I wanted to just talk about how compound interest is exponential growth. Compound interest is something that you'll see when you try to deal with some money stuff. You can see that this orange compound interest graph right here grows and increases speed, where a simple interest graph is more linear, so it follows more of a line. So simple interest means like there's a percent and it gets added the same amount every month or whatever. Compound interest means that a percent of the balance gets added each time. So that's why it grows exponentially. So what I want you to do right now is I want you to go to Desmos, maybe on a separate tab, and just type in this thing, y equals ab to the x, and then you're going to click the button that says all when you have a slider that shows up as an option. So I'm going to actually switch to that on my screen too, so that you can kind of see what I'm looking for. And I want to do a little bit of experimenting with that. So here I go. I'm just going to type in y equals a, b, and then to the x, to do a exponent, you can do shift and then 6, and then an x. You have to click that all button. And then we just have to change a and b to different numbers to kind of see what the graphs look like. So I'm going to just change b to 2, and maybe I'll change a to like 0.5. And I can see that as I change all of these things, the graph changes a lot every time I do that. So if I make a bigger, I can see that those A's kind of connect to where the graph is crossing on the y-axis there. And then I see the bigger the B that I make it, the steeper it gets. And then if I make B between 0 and 1, I see that it starts to go the other way. So this graph is exponential decay. And then this graph is exponential growth. So those a, b to the x graphs are what we're going to kind of try to start building our understanding of today. And we'll go from there. Okay, so here we go. I'm going to have to go back and forth between my Desmos graph and this slide because I need to make sure I understand how these things connect to each other. What I did notice was that when I put in different values for A, I noticed that the y-intercept was whatever that A number is. So I'm going to write the point 0A as my y-intercept. And so I'm going to look at that again and just make sure. So if I change A to -1, see how it crosses at -1 then? And so that shows me that that negative value and a positive value, no matter what it is, that A value tells me what the y-intercept is. So that's great. All right. I noticed that there's something going on over on the left side of this graph, and so I'm going to change my A back to like 1 just for now. Okay. And what I notice is there's this like invisible line that this graph never really touches or crosses. If we go further over here, it looks like it's starting to get really close, but then as I zoom in, you can start to see that there actually is a little bit of a gap there, even though I'm way far away. Do you see that gap now? Well, now I can see, okay, actually, even though I'm really zoomed in, there is a distance between the graph and the x-axis. So that's really important. That line, the x-axis right now, is what we call a horizontal asymptote. We have not really heard that word before, so I'm introducing a new vocabulary word. An asymptote is just a line that a graph does not ever cross, but it gets closer and closer and closer to it. So I'm going to write that down for a second. But I noticed that that line was always at y=0. No matter what my graph is, if I change the A, it's still at 0. If I change the B, it's still at 0. And so even this one, when it's decay, it still goes to 0, but just over on the right side this time. So that's kind of interesting. Okay, so our horizontal asymptote, I'm going to just underline the word asymptote and write line that a function approaches but doesn't cross. Okay, so there's a little quick explanation of what an asymptote is. Okay, now I need to figure out when is it exponential growth. So I'm going to try to make my graph look like exponential growth again, and I notice that it's any value for A. A doesn't really matter so long as A is positive. See how that's growing left to right? But then B is really what makes a difference. So it becomes decay, it looks like, when B is below 1, and it looks like B makes it growth when B is greater than 1. So I'm going to summarize that. Exponential growth happens when A is greater than 0 and B is greater than 1. Exponential decay happens when A is greater than 0 and B is between 0 and 1. Okay, great. Now we need to think a little bit about the domain and range. So what I notice is that no matter what x values, no matter what my a and b are, it really looks like the x values are always defined. Like there's always an x value all the way over here, and we saw that with that asymptote where we scrolled way over and we saw that it was still there. And then if we follow this up, you'll see that this continues to grow and grow and grow at like forever, but it's just that we just have to keep growing faster in the y direction, but it does actually keep going in the x direction too, and you can kind of see that as you scroll. So that's interesting. But what that means is our domain is all real numbers, and our range is y is greater than 0. And I know that it's y is greater than 0 because of that asymptote. So as I scroll in, I get closer and closer to 0. I never cross 0, and so the range is getting closer to 0, but it never hits that value. So we say that there's an asymptote there, and then that makes the range y is greater than 0. Okay, we aren't going to look a lot at when either a or b are negative. It just gets really weird, and it's not really something we need to do in Algebra 2. Okay, so I want to do a little graphing. I want to sketch some graphs. And I know based on what we did in the last slide, some information. And so what I know is that this 3 is the A, and the A tells me the y-intercept. And so the y-intercept is the point 0, 3. And so if I sketch my graph, it looks like 1, 2, 3. there's going to be a dot right there because of the y-intercept, okay? This b is a growth rate, and so b is greater than 1, so we have exponential growth. And so this graph should look something like this. There's a pretty rudimentary, but an okay sketch of this graph. Tomorrow when I see you next, we're going to spend a little bit more time on like how do we actually make these graphs look really nice and really precise. But for today, I just want to know, okay, this is growth and the y-intercept is 0, 3, and so I can kind of sketch that graph pretty well. I also am going to know, based on what we talked about today, that I have a horizontal asymptote at y equals 0. Okay, let's do another. I'm going to scroll this down a little bit so you can actually see the numbers. This time I have a equals 729, and then I have b is 1/3. And because b is between 1 and 0, I have exponential decay. And what that means is instead of it growing like this, it actually shrinks like this. So the graph is going to look like that. So we have a y-intercept at 0, 729, and the exponential decay says, okay, well, instead of growing left to right, we're just going to be decreasing left to right. So I'm just going to put a dot here and call this the point 0, 0, 1, 729. And then I'm going to, because I know it's decay, I'm going to start high and I'm going to go lower like that. And so this graph is going to look like this. I still have that same asymptote there like that. Okay, sweet. Let's do a little algebra. And in this algebra, we're going to try to actually write the equation, try to figure out what a and b are. So the cool thing about this is that, well, like, I know that a relates to the y-intercept, and so I can just look at that and say, okay, well, a must be 1/4, 0.25, 1/4, whatever, both will work. The thing that's a little bit trickier is that we have to solve for b, and we're going to have to use this coordinate to figure out what b is. So I know right now that I have y equals 1/4 b to the x. Well, I have this coordinate right here. So this is the x value and this is the y value. So let's put in 4 for y and 4 for x. Okay, well, how do I solve for this? Well, I must have to, like, what? Let's see. Divide both sides by 1/4 or multiply both sides by 4, because the 4 will undo this. So then I'm left with b to the 4th equals 16, because 4 times 4 is 16. And now I know, based on last unit, that if I solve for b, I need to take the 4th root of both sides. And the 4th root of 16 is just 2, so b equals 2. So now I know this number also, that's 2. So my equation is y equals 1/4 times 2 to the x, and there it is. Nice. Okay, one more. Same deal. This is a, tells me exactly. A equals 72. And then I have this point right here that says x, y are 2, 8. So we're going to do the same process. Y equals 72 b to the x, and we're just going to put in the 8 for y and the 2 for x. So here goes. Not y, 8 equals 72 b to the 2. Okay, so then divide both sides by 72. I don't know what that is. Let's do 8 divided by 72. Okay, that's this 0.296. Wait, I did 27. Oopsies. 72. My fault. 0.111111. Hey, that looks like 1/9 to me. So I'm going to say 1/9 equals b squared. So then b equals 1/3. You can check that. The square root of 1/9 is 1/3. So, okay, so now I know b is 1/3. So I can rewrite this as y equals 72 times 1/3 to the x. And there's my answer. Okay, so then I guess the question is way back at the beginning of this video, which is getting very long and I'm very sorry. We talked about this formula and I said, oh, that R is an interest rate or a percent increase. And so I want to talk about what this thing is that I'm representing with this equation. This 500 is, by the way, this equation is f of x equals p times 1 plus r over n to the nt. So the p is principal, first value. Amount, I forgot how to spell. P is your starting amount or principal. R is an interest rate. In this problem, it's 2%. This 12 is n, and the n is the number of times per year, let's say, the interest is compounded. So that means that like through the year, 12 times evenly spaced, oh wait, that's once a month, the interest is calculated. So it's like on January 1st, you get interest calculated. On February 1st, interest is calculated. On March 1st, interest is calculated, and so on. And so every month you get interest added to whatever account it is that you're looking at. And then the T, oops, I'm going to do that in a different color. The T is just a time. So like if I ask you how much is in the account after 5 years, you're going to put in the value for T. Okay. So quickly, what I see is I have 1 plus something right here, which means that that B value, that whole thing is just a B, but B is greater than 1 here. So I have growth. And I have this 500 starting value right here. And I have, so that means that I'm starting with a 500, the y-intercept is 0, 500. So this graph is going to look like, here's 500, and then we have growth. So it's going to look like this. So over time, this money increases a certain amount of time, certain amount. Okay, so it says the question is 5 years from now. So we're going to put in 5 for x, and we're just going to evaluate that. So I could even do that in Desmos. I'm going to do that real quick. This is just something that we can type in. I'm going to type in 500 times 1 plus. And then if you do a divide symbol, like the slash next to shift, it'll make a fraction. It's 0.02, and then 12, and then to the, whoops, 12 times 5. Okay, and so we find out that in 5 years, we will have $552.54. All right, there we go. That's the last example. Here's the deal. You have a book assignment. There are books in the back corner of my room. I want you to do all these problems. For the first set, I want you to just try to sketch graphs as best as you can. And then there's 3 more problems at the end. Try all of them, please. You should have time in class. And then tomorrow we'll do a little bit more graphing. We're going to clean up some of the stuff that we learned today, and then we're going to move on with our lives. Have a great day. I will see you tomorrow.